Here's some notes on what's going on with problems 1.4 and 1.5. We have an amplifier, but it has two inputs instead of just one. Well, we all know that the gain is A, V out over V in. Well, we have one gain, that's AA, V out over VA. We have another gain, that's AB, V out over VB. Well, that's nice, but how do we actually find that? Here we go. We all know that when you have multiple inputs and a single output, we can use our favorite technique, superposition. And we do that, we find the output in response to VA for this case. We get something times VA. We do the whole analysis again. We get something times VB. Superposition says we can just add those outputs together. That's really nice, but we're trying to find the gain. What is that really? Well, it's V out over VA. That would be one of the gains we're looking for. Plug that into our equation here. We get this something here, question, 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 and that's really nice, but whoops, plus this other thing, VB over VA with a little bit of algebra. Yeah, well, I don't like this because what is this term? It has VAs in it and whatever. This is supposed to be the gain. Gain is like a constant, right? It doesn't have to be if our gain is dependent on something else that's actually going to be not linear. Well, we have to do something else about it. Well, what we do is, when we're talking about this gain thing, what we're really talking about is we're talking about a change in the output and for a given change in the input. And we're going to call the input VA for this time. Well, here's what we do. So we're going to erase this, draw, and we're ready to go. When we say change in for a change in, really, that is a partial derivative of the output, change in the output for the change in VA. If we take that derivative, this is actually an easy one to do. The derivative of this with VA is just this term out in front. And take the second term, derivative of that with respect to VA, and we get, it all goes away. Okay? So this term right here, that would be our AA, and that turned out to be this question mark, question mark, question mark. And there we go. That is our gain. The problem 1.4 and 1.5 is not asking for the gain with respect to one input or the other output. It views these two together, these two inputs together, and it views them in a different coordinate system. So instead of VA or VB or V1 and V2, it looks at the same and the different. So that would be VD and VCM. So all we have to do is transform this into this, and there we go. We can do that by just writing, well, we know what VA is. We can write that in terms of something VD plus something VCM. That's another test question, by the way. We can do the same thing for VB. We take that, substitute these two terms into here, VB and VA, or VA and VB. Now we solve this, V out as a function of, now it's some other term times VD plus some other term times VCM. We go back to a previous slide and we take the derivative with respect to the differential, derivative with respect to the common mode, and we're done. Really, we're technically, yes, we're doing the derivatives, we're doing that next week, but really we're looking for the coefficients here. So that's the gain with respect to VA, this is the gain from VB, or if we transform these two terms into differential and common mode, we've now found the differential mode gain and the common mode gain, and we're done. So really 1.4, 1.5 go together. You come up with one formula and find the coefficients of each. That's what we mean by gain. If you try to divide these algebraically, you don't end up with a good situation, and in fact you'll never get it. You'll never be able to get the VB out of your gain equation. which is why it just doesn't make any sense. But and that's also why we need to use the derivative. It's a change in one with respect to a change in another variable.